Here we go again. Let's draw more Haworth projections. This time around we'll do it for ketohexose sugars. So the one that I chose was psychose, the funny sounding molecule. So we have a ketone, right? This is technically position 2, but I am relabeling the carbons to start at the carbonyl carbon to ensure that we can say what kind of ring size we're going to get in the structure. So one possibility is that starting from the carbonyl carbon of this ketose sugar, we go all the way down to the final carbon, and that covers 5 carbons in total, which means that if we go straight to the oxygen of that uh, final carbon, we'll end up with a 6-member ring, and that's absolutely a possibility. Another possibility is that we stop at position 4 and then make a right and end up with the penultimate oxygen being position 5, yielding a 5-member ring. So we're going to look at both of those possibilities, but we'll start first with the pyranose version of this sugar. So like what we did in the previous example, you would take your ketone or your ketose sugar and you'll push it to the right so that it falls flat on its face, right? So the ketone is as far to the right as it can get when you push this thing from left to right and make it fall flat on its face. All right, so what happens, just like before, all the H's in psychose happen to be on the left side of the molecule. By the time you push this towards the right, the H's are now pointing up. All 3 hydroxyls were pointing to the right. By the time you make it fall flat on its face, the hydroxyls are pointing down. Okay, so for the alternative that comprises 6 atoms in the ring, starting with the carbonyl carbon as the pseudo first position and making our way across, it is the case already that the oxygen that's going to wrap around and attack the carbonyl is already in the horizontal position. So you don't need to rotate the last 3 groups at all. You have the OH exactly where you want it. So you basically go ahead and take that linear chain and you rotate it so that, well, not rotate it, you just bring it around to close the ring. And that brings us to the Haworth projection, which in this case, it will be a 6-member ring based on the second row element count that we had right here. So we draw that 6-member ring. Remember, on the upper right, we have oxygen. That's position 6. And if we move clockwise about the Haworth projection, we'll first hit position 1 again, right? So from the last position, we go back to the first position. And then going clockwise will give us the rest of the spots, positions 2, 3, 4, and 5. Okay, so what we do is we ignore position 1 for a second. And then we look at positions 2, 3, and 4. So we see that position 2, 3, and 4, the hydroxyls happen to be pointing down. So as you draw position 2, hydroxyl has to be pointing down. Position 3, hydroxyl has to be pointing down. Position 4, hydroxyl has to be pointing down. And then at position 5, notice that all we technically have is just 2 H's on that carbon. So position 5 is just going to be H and H, right? So there's no chirality really associated with that carbon. That's all you have on that carbon, just 2 H's. All right, and then position 1, just like with aldose sugars, this is where the carbonyl becomes an alcohol. So you go from being sp2 to sp3. So we're going to have 2 versions of it. We are going to be forming an OH group. But what I want you to notice is that attached to that carbonyl carbon is not H. So we're not going to end up with HOH like we did with the aldose sugars. Instead, at position 1, we have CH2OH directly bound to it. So what we're going to get at position 1 is going to be OH as one of the groups and CH2OH as the second group. And so you can draw it so that the OH ends up pointing down and the CH2OH points up. This will still be considered the alpha anomer because the OH functionality happens to be pointing down in this structure. If we draw the same ring again, but for position 1, we swap the order, so now OH is pointing up and CH2OH is pointing down, well, now we have the beta anomer, right? And as far as the name goes, because this derived from D-psychose, this is still a D sugar. is still psychose, but it's derived from the 6-member ring version of it. So we're not just going to say psychose, we're going to say D alpha to emphasize that this is the alpha anomer, and then we say psychopyranose, right, to really make it explicit that it is a 6-member ring that we're dealing with in this projection. Same thing goes for the beta anomer. So this is a D sugar, it's the beta anomer, and it's a 6-member ring altogether. So this is D beta psychopyranose. Okay, so just be a little bit careful with this one, right? Because the penultimate position, you do not have a group other than H, so you cannot rely on that to determine that this is a D sugar. You kind of have to go back to the original structure to make sense of that. Now, on the other hand, if we look at the situation where we stop at the penultimate carbon, we make a right turn to the penultimate hydroxyl, we're going to get a 5-member ring. And here we're going to have more of a hint as to whether the sugar is D or not, based on how the Haworth projection looks like. But first, we're going to address that this is a 5-member ring, so we'll have to use the word furan in the name ultimately. So just like before, we push this molecule to the right, make it fall flat on its face. The carbonyl carbon is the pseudo position 1, right? So we count 1, 2, 3, 4 carbons, and then oxygen. Now the oxygen that we are considering for ring formation, it's not on the horizontal, so we're going to have to rotate the groups to make position 5 be in the horizontal framework. So it looks like we have to go clockwise here, right? So move OH towards the CH2OH position. That will make it be horizontal. That means that the CH2OH position also has to move clockwise towards the H position, and H has to move clockwise towards the OH position. So ultimately, this linear rope will end up looking as follows. OH will now be in the horizontal, CH2OH will be on top, and H will be on the bottom. Okay, so that takes care of the last hydroxyl, right? It's on the horizontal. Now that that happens, we can wrap this around to form the ring. This will be a 5-member ring, and because we don't have a crazy, like big chiral thing sticking out of it, in this case, I have no issue with having the oxygen of this 5-member ring pointing on the upper right, which is the more usual way of drawing this, furanose ring structure. All right, so just like the previous structure, we ignore position 1 for a second, and then we label the ring, right? So the oxygen in the ring is the last position, which should be position 5. As you go clockwise around the ring, you should hit position 1, basically go back to the origin. And then as you move clockwise on the ring, you complete the rest of the numbering, right? So positions 1, 2, 3, and 4. So you ignore position 1 for a second. At position 2, OH is pointing down, so over here we'll have OH pointing down. At position 3, OH is pointing down, so at position 3 we'll have OH pointing down. At position 4, CH2OH is pointing up, so position 4 will have CH2OH pointing up. All right, and then that leaves us with position 1, which is where the variants are going to be encountered, right? The epimers, the anomers. So here, remember that we're talking about ketone, right? So position 1 will turn the carbonyl into a hydroxyl group, but at position 1 we also have CH2OH. So on the one hand, we'll have OH pointing down and CH2OH pointing up. And because the OH is pointing down, this is the alpha anomer. If you draw that same ring and simply swap the order, right? So OH is now pointing up, CH2 points down. This is the beta anomer. All right, now here is something you really want to be careful, especially if presented with the ring as the molecule of initial interaction. Because if you look carefully, you should realize that the penultimate position has a CH2OH. Position 1 also has CH2OH. So it's very easy to get confused by this. I've seen it in textbooks. I used to make the same mistake before. The hemiacetal carbon, the anomeric carbon, is only going to be the one that contains the CH2OH and OH as the two fragments, right? So don't just look at CH2OH and forget about the rest of the story, because if that CH2OH is coupled to a hydrogen, then you're not looking at the anomeric carbon, right? You do have to have that OH present in there additionally to CH2OH for this to be the anomeric carbon. Okay, but with all that said, we're going to name this thing. So we are looking at the D sugar. It's the D sugar because the CH2OH coupled to hydrogen happens to be pointing up. So this is the D sugar. And it is the alpha anomer because the hydroxyl at the anomeric position is pointing down. So this will be D alpha psychofuranose to emphasize that this is a 5-member ring, whereas the anomer will basically be known as the beta psychofuranose, right? And that's how you differentiate the two rings from each other. Okay, so one additional thing that you will have to consider, and this shouldn't take too long, so I'm going to include it on this video, is the chair conformation of sugars. Since we already talked about the tylopyranose sugars, I'm going to show you the alpha version and the beta version. But the reality is that this is not a true 3D representation of the cyclohexane ring, the oxacyclohexane ring, if you want to be technical. The true representation is actually a chair conformation. And what you have to kind of remember about this is that when you draw the chair conformation, the corners that point up in the ring will have an axial bond pointing straight up. The corners that point down will have an axial bond pointing straight down. So you should have, technically in total, you should have 3 down and 3 up, right? But one of the corners is going to be oxygen that doesn't have additional bonds. After that, you have to draw the equatorial bond so that you complete a tetrahedral structure. And you have to be careful for the middle carbons not to draw the equatorial position in such a way that looks vertical, right? It should be, slanted to one side specifically. All right, so what you do is you place that oxygen, the same oxygen that you have there on the 6-member ring, and then you proceed with everything else here. And what matters is whether the hydroxyl or the CH2OH is above or below the hydrogen. That's why you have to make sure that it's follow to the dot. And we're going to go clockwise around the cyclohexane ring, just like what we did with the Haworth projection. So at position 1, the OH is below hydrogen. So position 1, you have to draw OH below hydrogen, and it happens to be in the axial position in this conformer. Okay, but that's coincidental. But what is not coincidental is the fact that no matter what, the OH is in fact below hydrogen. That's the important thing. At position 2, hydroxyl is above hydrogen, so position 2 will have to have the hydroxyl above hydrogen, which means that this hydroxyl is also axial. And you may recall from OChem 1 that yes, being axial doesn't mean that you're above or below hydrogen by default. You really have to make sure by looking at it, this hydroxyl is in fact above H, and the previous hydroxyl is in fact below H, and they're both axial, right? So you can't just say, oh, if it's below hydrogen, it's axial. If you do that, I can guarantee you're going to get the wrong structure drawn on your cyclohexane. So you remember, below hydrogen better be below hydrogen, and above hydrogen better be above hydrogen. So case in point, position 3, hydroxyl is above hydrogen, so we make sure that the hydroxyl is above hydrogen. At position 4, the hydroxyl is also above hydrogen, so we make sure that the hydroxyl remains above hydrogen. And at position 5, the CH2OH is above hydrogen, so we make sure that the CH2OH is above the hydrogen. And that's how you derive the cyclohexane structure of this thing. Okay, so that's your D-alpha tylopyranose. And the same thing will happen with beta. In fact, everything that I did here on the left side of the molecule is going to be a repeat over here. The only difference is going to be that for the beta, at position 1, hydroxyl is above hydrogen. So hydroxyl better be above hydrogen, right? And that's really the only difference. So hopefully this is not too much of an ask from you to do. Because by the time you get to the Haworth projection, you should have everything you need, structurally speaking, to do this. So, if you need to refresh your memory with drawing cyclohexane chair conformations, you better do that, but become familiar with this method. And once again, above hydrogen means above hydrogen. Below hydrogen means below hydrogen. Do not deviate from that. All right, and just to drive the point completely, let me show you the same thing with the 5-member ring. In the case of the 5-member ring, we have what is called the half envelope structure, and it doesn't really change all that much from the Haworth projection. So usually most people will not bother drawing the half envelope structure because really this doesn't change all that much. But I just want to highlight what we did before. At position 1, OH is below H. At position 1, OH is below H. Position 2, OH is above H. OH is above H. At position 3, OH is also above H, and so we have OH above H. And then the big chiral group here is below hydrogen, so down here we also have it below hydrogen. So the same story happens for the anomer, where basically we just copy the red, pink, and green components exactly as they were here, but the only thing that changes is that at position 1 now OH is above hydrogen, so you just make sure to keep it above hydrogen. All right, and then that basically covers the chair conformations of these things. To show you the same story and kind of finalize it, we'll do it with the ketose sugar, cyclose specifically. So here, when you go to the cyclohexane, notice that position 1, CH2OH is above OH. So above OH, we have CH2OH. Position 2, hydroxyl is pointing down. OH is below hydrogen. At position 3, OH is below hydrogen. OH is below hydrogen. At position 4, OH is below hydrogen. OH is below hydrogen. And then position 5 is just two H's. So, just use draw two H's there. Same thing happens with the beta version. The only difference is that position 1, the OH and the CH2OH groups simply swap places, right? Now we have OH above CH2OH. Okay. And then your traditional 5-member ring of ketose sugars, same idea. If you draw the half envelope structure with the oxygen pointing up, CH2OH is above OH, so CH2OH remains above H. H is above OH, so H is above OH. H is above OH for the blue component, H is above OH for the blue component. And then the last one, we have CH2OH above hydrogen. So we have CH2OH above hydrogen at position 4, excuse me. And that's basically the same story right here for the beta anomer. You simply copy and paste this thing, and at position 1, you simply swap the order, right? OH is now above CH2OH. And that basically does the trick. Okay, so yeah, this video contains quite a bit of information, so we're going to stop it right there. And in the next one, we're going to start talking about the reactions that you can actually do with sugars. So catch you in the next video. Bye bye.